Okay, that's 1. 1, 1, 1, 1. That is a 4-bit binary number. I should probably mention, I'm going to use that for a sequence detector. So the one we did yesterday was 1011. Yeah, I know, it's a good one. But okay, fine. There. Yeah, I didn't put that in there. My bad. And 1111, we can do that one. It's a good one. My cat just woke up, so he's very hyper right now. But wait for some more people to get in here. It's still early. Yeah. I don't know why my camera's glitching out like that. Hopefully that doesn't happen too often. Two people in there. I think one of them is me. I'm not sure. But so how is your, I guess, final week of actual classes going? Whoever is all in the chat. I asked about finals yesterday, but I was told that finals doesn't start until next week. I sent a message on my class group chat. Oh, thank you. Thank you so much. Let me see if I'm going to share the link, or try to share the link on the Discord, at least in the tutoring room. Preparing. Oh. Okay. Cool. Three people, now it's a party. Set my phone and do not disturb. I have it right next to the microphone, so I don't want it to buzz you all whenever I get a text or something like that. Do not disturb. Cool. Someone reacted. Eric, of course, yeah. I guess I'll give it until 6:05. I guess I'll get started. It does look like a less delay than I did yesterday. At least that's how it looks right now. Yeah, because I just pointed on the screen, so yeah. It should be a bit faster for you all to get back to me, or if you have any questions than it was yesterday. Are you gonna sit down there for the whole review, buddy? Are you? Four people. Nice. Okay, well, I guess we'll go and get started. Looks like there's 4 people. Eric wrote 1001. Good evening, Eric. 1011. No, Eric, I think that was one we did yesterday. So we're not going to do the same one twice. We'll do the 1111. That's fine. Detecting 4 ones in a row, it's still a sequence detector. We'll still get everything we need out of it. See, this was, I think, for Dr. Balsara. I think there's so many professors there, I can't keep the name straight. I think it's Balsara. So, anyways, the first thing on his email was sequential circuit design. So we're going to do an FSM. And we're going to do the sequence detector. And we're going to detect 1, 1, 1, 1. All right. In yesterday's review, I got into the identities of Boolean algebra and things like that a little bit. So it wasn't in his email like it was in Dr. Irani's. So I'm not going to cover it as much or at all. If you have any questions about Boolean algebra, just check the first, I guess it's about 15 minutes of yesterday's review. I get into all that stuff, but Yeah, we're just going to skip right to the sequence detector on this one. So if our sequence is 1, 1, 1, 1, first thing we do is always we start at state A, output is 0. All right. So we start at state A, and first thing we do when we're given a sequence detector is find our, the case that gets us what we're looking for, which is obviously inputting 4 ones in a row. So for state B, we're going to get there by inputting a 1. For state C, we can get there by inputting a 1. For state D, we're going to input a 1. And for state E, we're going to input a 1. All right, so state E is the final state, and it's the only state where we've detected the sequence, so it's the only one we're going to output a 1. All right, I should mention x equals input, x is the output, and we're going to call the input B. All right. No questions so far, cool. So far what I've done is I also need to assign states or outputs to all the other states. All right. What we've got is anytime we input a 1, we move further into the sequence until you've inputted 4 in a row, in which case we input a 1, or we output a 1. All right, so this is everything passing, or this is our past case. Next we need to consider what happens in these states if we input a 0. So if you input a 0, you're going to go back to state A. Or if you input a 0 when you're at state A, you can't move forward. So you kind of just have to stay at state A. If you're at state B, I was just not realizing this is going to be a... All right, if you want more FSMs, go look at yesterday's stream. I do a different one, but yeah, a lot of these are going to follow the same pattern. If you're at state B, you input a 0. So to get to state B, you inputted 1, 1, and then you're looking at this next state, this next input. Okay, so you don't know what happened before, but you know you've inputted at least a 1 before. So if you input another 1, you go obviously on to state C, that's putting in 2 ones in a row. If you input a 0 when you're at B, then this doesn't line up with any part of our sequence, so we have to start back over at A. All right. So similarly with C, in order to get to C, you don't know what you've done before, but you know you've inputted 2 ones in a row. And then you're looking at what happens next. And so we know if you input another 1, you go down to state B, but if you input a 0 here, this is no part of our sequence, so we have to start back over at A. All right. Still no questions, cool. If you have any questions, you can put them in the YouTube chat, and I'll also be looking at the whiteboard on Discord, just so you know. But yeah, so if there are any questions and it gets delayed, I'll run back and cover it, but yeah, other than that, I'll just keep moving on. All right, so yeah, if you input a 0 when you're at state C, you have to start the sequence back over again, which means starting back at A. So next we look at state D. You know what happens if you input a 1, you go to E, but if you input a 0 when you're at state D, what that looks like is inputting a 1. So to get to D, you had to input 3 ones in a row. And we're looking at what happens here if you input a 0. And this again is starting over the sequence again, so you go back to A. I decide if I want to go through that. I'll go around this way. Like that. All right, so that's state D. Next, we look at state E, and we look at what happens. So we don't know what happens if you input a 1 or a 0 at state E. All we know is to get to E, you had to input 4 ones in a row. Cool. And then let's consider if you input a 0. If you put a 0, then you're back to starting the sequence over again, because this 0 is no part of this sequence. So if you input a 0, you go back to A. However, if you input a 1, well, this 4 would have gotten you to E. Suddenly, this 4 now gets you to finish the sequence. So if you input a 5th one in a row, that's still 4 ones in a row. It's just a different 4 ones, so you don't use this one anymore. So if you input a 1 when you're at state E, you actually stay at state E. All right, so hopefully that makes sense. If you need me to talk about that more, I'll go back and do that. But so far, I don't see any questions. But, yeah. So, on the Y erase production sequence. So the first thing I do whenever I think I'm done is I check for exclusiveness and completeness in a finite state machine. So exclusiveness means that for every input you give at a state, it sends you to no more than one place. So if I'm at state A and I input a 0, the only place a 0 will send me out of state A is back to A. And if I input a 1, then the place that will send me outside of A is over to B. Right? So you can do that with all of these states. At B, if you input a 0, the only place it'll go is back to A. The only place it'll go if you input a 1 is to C. So yeah, so that's checking for exclusiveness. The other one is completeness. And that's saying that if I have any input, it's gonna have some place to go. All right, it won't be, I gave it an input and it has no idea where to go. And so what that looks like is kind of the same thing where if I input an A, it's not like I don't have any options of where to go. The only option I have is back to A. So that's how you check for exclusiveness and completeness. One thing I didn't do yesterday is I didn't give an example where it breaks that. So if I have some state 1, or I'll just call it S1, S2, and S3. And let's say I have 2 inputs this time. So X and Y. So let's say to get to state 2, my input X needs to be high, and to get to state 3, my input Y needs to be high. Now this is neither exclusive nor complete. It's not exclusive because if I input X equals 1, Y equals 1, then suddenly both of these paths are valid, and it'll have 2 destinations where it could go. All right, so that would be an example of it not being exclusive. It's not complete because if X equals 0 and Y equals 0, then neither of these paths are valid, and it has nowhere to go. So that's a place where the exclusiveness and completeness would come into effect. So hopefully, I'm I'm not sure how many classes actually cover that, but whenever I took DC, they hammered on exclusiveness and completeness quite a bit. But I don't know what your professor hammers on very hardly, so I'll just, cover it just to be safe. Let's see here, sequential circuit design. So the next thing I'm going to do is I'm going to go ahead and do the state minimization now. I technically have that next on my list, but I'd rather do it now that I still have the finite state machine or the state diagram drawn. And then we'll come back to designing the circuit. I will say now that this, as it is completely minimized, but we'll go ahead and do it for the fun of it, just so that you see the process of the tabular or implication table, whatever it's called, tabular method, the chart, the way you minimize state machines. So I'm going to do that on the next board. Ah, yes, my cat's experiment on humans. The result was 42. It's the answer to life, the universe, and everything is 42. Still no questions in either place. Nice. All right. So to set up your implication table, first you need to, starting at B, go through all of your states. So B, C, D, E. And then on the bottom, write all of your states starting at A up to the second to last state. And so basically every one of these boxes represents a check of equality between states. So obviously we don't have any checks between B and B. Like that would have been this block here, because we know B is always going to be equal to B. I think that's called the transitive property. So the first thing we always do whenever we make this, before filling out any of the blocks inside, is we check the outputs. So the outputs are equals 0. One. So remember from our state diagram, the only one of these states that had an output that was 1 was state E. The rest of them were all output of 0. So that's why output E is the only, or state E is the only one that has an output of 1. The one thing you can always do is cross out states that have different outputs. So E can never be equal to A because they have different outputs. So we cross that out. And we actually cross out this entire row for the same reasons. Again, every one of these has outputs of 0. State E has an output of 1. So E cannot be equal to anything. It's basically what we've decided. Let's see. Next is we start filling out the table. So what I'm going to do, or the way I like to always do it is, or what do I like to always do? Okay, on the left, so on the left here, I put the different states that this this bottom one will go in. So this whole column on the left is going to have the same values because they're always going to have the states that this the bottom state goes to. It's easier to just show you than to explain it. Oh, so that means the rest is valid. No. Or yes. No. It just means that those are the ones that we can. So I think what you're saying is that since we haven't crossed out anything else out, that they're valid. No, it means that we haven't proven that they're invalid yet. So the ones that have the x's right now are the ones that we were able to say are not equal solely based on their outputs. The rest of them, we haven't checked yet. And I'll show you the process of checking them. Basically what we're looking for is equivalent states. And since some of these states had different outputs, that was the quickest way to, yeah, they're maybes, exactly like you said. Yeah, they're maybes. And I can tell you right now, they're going to end up being unequal or non-equal, but we haven't proven it mathematically yet, or methodically. I don't want to call this math, really. But yeah, so what I'm going to do first is I'm going to look at state A. I'm going to see where it goes. If I input a 0 to state A, it stays at A. If I input a 1, it goes to B. So the way I do that is on top I put 0. So if it's a 0, it goes to A. If I input a 1, it goes to B. And for this entire column, I'm going to put the same thing on the left. A, B, A, B. Okay? So next I'm going to look at state B. So state B, if I input a 0, it goes to A. If I input a 1, it goes to C. So I'm going to put A, C. All right, so this is the row that has B on it. Now for the column that has B on it, I'm going to put on the left side. So A, C, A, C. All right, so you kind of see how I'm filling this out right now. If it's the block that corresponds to the row, I put that on the right. If it corresponds to the column, I put that on the left of the block. I picked those directions arbitrarily. It's just important that you have in your mind which one it is. If you want to swap it up, you can, but just make sure that all of your columns put their next states on the same side as each other. So I always put columns on the left, rows on the right. Next is C. So if it's a 0, it goes to A. If it's a 1, it goes to D. So A, D, A, D, A, D. All right, and next is state D. So if it's a 0, it goes to A. If it's a 1, it goes to E. A, E, A, E. So far, no questions that I see that are new. I don't need to flip you over anymore. I'm done with you. All right. So I could go the quick way and start at the bottom, but I'll start at the top just to show you kind of the process that I go by here. So if I see A next to A, that's good. And next I check B next to C. So I look where B and C intersect. So B and C intersect there, and I haven't crossed it out yet. So we can't cross this guy out yet. Okay? Next I'll check this block here, A versus A, B versus D. So I don't need to check A versus A, that's always good, but I can check B versus D. So B and D intersect right there, and we haven't crossed it out yet, so far so good. Next I'll check A versus A, we don't need to check that, that's always right, but C versus D, we haven't crossed that out either. So far these three are still maybes. We can't say officially that they're right yet. We can only say it at the end if we can't cross it out anymore. But so far those are maybes. Next we're going to check is this one here. So we have A versus A. Again, we don't need to check that. B versus E. B versus E, we've already crossed that out. So since B and E are not equal, this state cannot be equal. Okay? And in fact, we can look through here and we know that E isn't equal to anything. So any state that says something is equal to E, we know it can't be true. So both of these have, this one said C is equal to E, this one says D is equal to E. And we know that neither of those statements can be true. So we have to cross those out. And now we start back at the top. So here we have A versus A, and B versus C we need to check. So B versus C is still good. All right, we haven't crossed out yet, but down here we'll check B versus D. So B versus D, we crossed that out last time, so now we can cross this one out. Second pass through, we're starting to cross out some more. And C versus D, check that one, it's crossed out. That one goes away. This one checks B versus C, which was this block here, which is now crossed out. So we crossed everything out, which, like I said, we were expecting a fully minimized binary state machine to start out with. So this is, I think it's called implication table. I think it's called the tabular method. I really don't know. This is just the method I use to minimize state machines. Take a drink real fast. I still don't see any questions, so I guess this is all good so far. But basically what this proved is that we had a fully minimized state machine to start out with. Okay, I do have an example that does actually have some states disappear, but I'm going to get back to finishing up the circuit design of the sequence detector. So I'm going to go ahead and erase all this. And start. I'm going to start building up my truth table for my combo logic. All right. So what we're going to have is current state. So S2, S1, S0, input B. Zero. Can you tell I've done this a few times? Alright. 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 1, 1, 0, 0, 0, 0, 1, 1, 1, 0, 0, 1, 0, 0, 3, 4, 5, 6, 7, 8, 1, 2, 4, 5, 6, 7, 8. Alright, check. No questions yet. It's not a related chat, okay. Okay. So what I've got here is a setup for a truth table, and some things that we're going to be looking for are the next state. So we're going to look for next 2, next 1, next 0. So these 3 bits are going to represent the next state, and we're also having output X. All right. So these 3 bits here, S2, S1, S0, represent the current state. B represents the input. N2, N1, N0 represent the next state, and X is the output. Okay. What I'm going to do off to the side here is I'm going to label these states as, well, what I named them earlier. So we have A, B, C, D, E, and we stopped there. Because it only took 5 states to get there. All right, so we have states A through E, right? So states A through E. You know, every group of 2 here, as far as S2, S1, and S0 is concerned, it doesn't change. The only thing that changes within each of these groups is the input B, which we expect. So that's kind of why I set up the truth table like I do. For that reason. So next we got to look at is, well, we can go ahead and assign outputs. So for state A, the output is always 0. Actually, it's 0 in every case except for E. All right. Anything below E, we're going to assign don't cares for everything. So don't care, don't care, don't care, don't care, don't care, don't care. All right, because if we build this right, it's never going to enter, or the state register is never going to enter these values. One thing I should mention is I used 3 bits for my registers because I knew I had 5 states. And in order to represent the number 5, or to have 5 possible combinations, you need at least 3 bits to do that. So every state needs to have a different combination of bits for their state register, and you need 3 bits at least to get 5 different combinations, which ends up being 0 through 4 in binary. Okay. So now all that's left or missing from this truth table is the next states. Okay, so one thing you might have noticed from before is that anytime you input a 0, you go back to state A. And that's true for every single state here. So I'm just going to fill those out really fast. So 0, 0, 0. All right, so state A, if you look at the state register, it's represented with 0, 0, 0. And so what I've done here is, in the top part here, we'll notice corresponds to state A, inputting a 0, the next state will be 0, 0, 0, or state A. Similarly, if you're at, I don't know, state D, so the current state is 0, 1, 1, you input a 0, so that means you're going to go back to state A, which is encoded as 0, 0, 0. All right, so that's good so far. Next thing we notice is that with this particular sequence, anytime you input a 1, you go to the next state. So state A goes to B, B goes to C, C goes to D, D goes to E, and E stays at E. That's important to note also. So if you input a 1, you go to the next state. So if you input a 1 when you're at state A, you go to state B, which is encoded as 0, 0, 1. If you're at state B, you go to state C, which is encoded as 0, 1, 0. If you're at C, you input a 1, you go to state D, which is encoded as 0, 1, 1. If you're at D, you input a 1, you go to state E, which is encoded as 1, 0, 0. And if you input a 1 when you're at state E, you stay at state E, which is also 1, 0, 0. All right, let me check. Still no questions, so we're good. All right. So this is our truth table for our finite state machine. Cool. Next thing we'll do is solve for the equations for each of these. So, just generally speaking, in a finite state machine, or the general structure of it is you have some input, or you have some block of combo logic. It has the input and output, some the next state register values that get fed into a state register, which feed back in the current state. So this is going to be the same for every finite state machine you build. The only difference is really going to be what happens in this combo logic part. And that's what we're going to solve for. How fun. So what we get out of that that finite state machine, or the truth table in the back, was 4 different equations. And we'll solve for them one by one. So the first one we'll solve for is N2. So the next state 2 register, or line, or output, or whatever we want to call it. It's going to have inputs S2, S1, S0, and B. We set up our K-map. Again, if I'm going to just assume that K-maps are good for everyone. If not, I did some yesterday on yesterday's video, so I'm going to kind of gloss over doing these, but if you need the review, you can go back and watch yesterday's video. Again, I did it fairly close to the start of the review, so you know, it'll be somewhere in the first 30 minutes, I think, somewhere in there. All right, so now I start filling out this K-map with the N2 values. So that's this column here, which we have a 1 at state 0, 1, 1, 1, so that's 7, and then 1, 0, 0, 1, so 7 and 9, and then don't cares for 10 all the way to the end. So that looks like is 7, it's right here, so 7, here's 9, and don't cares everywhere else. So if we're going to minimize this, we're going to group this up together and this up together. And so we can say N2 is equal to, so this whole group here, what's in common is S2 is 1 and B is 1. So S2, B, 4, and then we look at this group 2, S1 is always high, and then S0 is high, B is high. So S1, S0, B. No questions yet, cool. So we can consider N2 minimized at this point, or we can say that this is our equation to find the second bit of our next state, or the third bit? Bit number 2 of the next state. All right. So bit 2 of the next state can be solved with this equation. Next one I'll solve for is N1. So N1. S2 is 1, 0, B, 0, 0, 1, 1, 1, 1, 0, 1, 1, 1, 1, 0. Alright. Make sure my cat doesn't try to jump on the desk. Okay. So N1, or next state, bit 1, is going to be at, this is number 3, so this is bit, or min-term 3, 5, and then X is all the way down after 10. So 3, 5, so 3, 5, X is all the way around here. All right, so no groups of 4, so just have this group of 2 and this group of 2. Make sure there's no questions. Good. Okay. So, and 2 is equal to, this is going to be S1 S0 naught B. And this is going to be S1 naught S0B. And this is supposed to be 1. Cool. Let's see, next one we'll look at is in 0. See how much of this I can erase, not ruin everything. We know the don't cares are all going to be in the same places. Now we're going to look at in 0, so that's place 1, 5, 1 and 5. Nice. So here's 1, 5. Okay. So we can circle that, and this one is all on its own. That can't get grouped with anything. Oh. Wait. You're probably going to let me have it in the chat. It's actually there. So instead of this group, I would group these two together. Okay, so far they haven't let me have it, so I think we're good. So yeah, it's just this one group because it's 1 and 5. I don't know why I marked 0, but yep. Hey, set that. You'll have a review later. Okay? All right. N0 is equal to, so this one here is going to be equal to S2 naught S0 naught B. All right. And then last one is the output. All right. So I'm not going to bother writing. Again, I kind of explained this yesterday. Because the output actually ends up being the same thing, where it's just equal to S2. All right, so if S2 is high, then the output is high. So the rest of these are don't cares. So the rest of the time that S2 is high, we don't care, except for this one case where we do care and it's 1. So for S, or for X, it's just going to equal S2. All right, so let me erase my key map, and we'll start drawing this. Here. Okay, so we've got combo logic here. State register, input, output. And come back around, we're going to have three lines that correspond to the next states. Going back in, we're going to have 3 lines that correspond to the current states. And inside, we're going to have combo logic. So I'm just going to do the first one of these because if you saw yesterday's video, it got kind of ugly. So we're just going to do one of these just so you get the idea. Because eventually inside of there it gets pretty messy with all those logic things going on. So we'll do N2. So I'm just going to say this is S2, this is S1, this is S0, this is going to be N2, N1, N0. So you follow these lines back around, this is going to be N0, N1, N2. This is going to be my output. Or, sorry, I call that X. Okay. So inside of here, I have 2 AND gates that get ORed together. So and the output gets sent there. What goes into these AND gates is going to be, the first one's going to be S2 and with B. So it's going to be S2 and B. The next one's going to be S1 and S0 and B. So there's B. There's S1. There's S2, or S0, I should say. So this AND gate corresponds to this one. This top one corresponds to this one. They get ORed together, which is, or I shouldn't circle that OR because it looks kind of extra now. But they get ORed together and get sent into N2. And that in turn gets fed back into the state register. Okay, no questions yet. So I basically repeat this process for N1 and 0. X would be a simple one, so X is just equal to S2. So this line here is S2. So all I would do is just grab it there and send that to X. All right. So that would be my output. So I've technically done 2 of them. So you'd have, you just have to continue doing that for N1 and N0. And then that'd be your combo logic part of the finite state machine, which is really the only part that's different for every finite state machine. All right, so I'm not seeing any questions yet. I'm also not seeing any viewers. They haven't really dropped off. Wow. Oh, 1 viewer. Oh. So yeah, next thing I've got on here is timing. Okay. So let's see, if I was doing this, so I'm going to go and erase all this stuff. No, we're still here. Well, okay. Timing diagrams, yep. Okay, so next we're going to do is time diagrams. Let's go ahead and do it for that last circuit that we had. So imagine we have a sequence detector like this. So let me draw this in a different color. So we'll have input B. This is going to be our state. Actually, this next one's going to be our clock. this one's going to be our state. This is going to be our output. Okay, so I'm going to draw a clock signal. What do you want? All right, how many? 1, 2, 3, 4, 5, 6, 7, 8. Okay, yeah, count right. So I have 8 clock edges. So let's imagine that we inputted the sequence 0, 1, 0, 1, 1, 1, 1, 0. So imagine we send this sequence through. So first thing we do is we mark our clock edges. And I'm just going to always do it on the positive edge of the clock, the rising edge. In Verilog, we would call it pos edge. Okay. So there's that. And then right here, I'm going to draw this, what this would look like. So the first input would be a 0. All right, then I would change to a 1 before the next clock edge. Then I would change back to a 0 before the next clock edge. Then I go up to high for the next one, 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 and then low for the next one. All right, so I'm kind of just making this up as I go, but I clearly see here, I see the sequence that's in there. What you would expect is you don't really know what happens here, but we know as soon as we get to this clock edge, we've inputted 0. And you remember that every one of our states, if you input a 0, goes back to the start. So, or does it matter which edge you mark? I picked rising edge. Your professor should tell you which edge they want it on. I know whenever I took it with Dr. Kogan, it's kind of just a thing in her class that it was always the rising edge. That's just how we always did it. But yeah, so. Okay. So I always consider rising edge triggering edge. I think Dr. Dodge, if any of you had him, he always used falling edge as the triggering edge. Okay. It's not supposed to be the hard part of the problem. So if you have any questions about it, ask your professor, and they should just tell you which edge you're going to use. So normally, which edge you use isn't the meat of the problem. So I'm going to use a different color. I'm going to use green for the current state. So that's what this is going to represent, is the current state. So you input a 0 to this sequence detector, you expect to go back to state A. So right here, we're going to be in state A. We're going to be there at least until the next clock edge. Now notice this transition, I have it starting at the clock edge, which means that technically this A doesn't happen until sometime after the clock edge, and that's more realistic with how circuits look. There's going to be some delay after the triggering edge before the circuit actually catches what's going on. Because again, that's the whole point of having a trigger, is that it's telling you when to start doing things, but real circuits don't happen instantaneously, so it's going to take a little bit of time to reach where it's going, and we know it can't even start until we actually trigger it. So yep, that's right, buddy. So next clock edge, we input a 1. So if you input a 1 to this sequence detector, remember we would go to state B. I don't still have it. Actually, I kind of do have it right here. Watch your head, buddy. Yeah. So if you're at state A, you input a 1. Next state you go to is state B. All right, 0, 0, 1. That's what we encoded as 0, 0, 1 for state B. So for here, we would transition to B, at least until the next clock edge. All right, if you're at B, if you input a 0 at this clock edge, here you input a 0. So if you input a 0 when you're at B, so you're at B, you input a 0, you go to state 0, 0, 0, which is A. So next state you go to state A. So no new questions, cool. So you're at state A for at least until the next clock cycle. Now, if we're at state A, you input a 1. We already looked. We know we go to B at this point. All right. If we're at B, if you input a, so we're at B, we're looking to see what happens when you input a 1. Right, so this represents a 1 at the clock edge. So if you're at B, you input a 1, you go to state 0, 1, 0, which is state C. So state C. If you're at state C, we're going to look at what happens when you input a 1. All right, so we input a 1 at the clock edge. What happens if you input a 1 at state C? So state C, input a 1, you go to state 0, 1, 1, which is state D. All right, if you're at D, we'll see what happens when you input a 1 at the clock edge when you're at state D. You go to, so D, input a 1, you go to state 1, 0, 0, which is state E. All right, and the last clock edge we have here is at state E, and we input a 0. So if you're at state E and you input a 0, it'll go back to state A. So 0, 0, 0, which is 0, 0, 0 corresponds to A. All right. So we have our states all filled out. I forgot to mention this earlier, but the way we designed it was like a Moore machine. Oh, it's under the table. Nice. Which means that the output is tied directly to the current state and has nothing to do with the input per se. The input affects what the next state's going to be, but it doesn't affect the output. Which means that whenever we draw our output line, we don't even have to consider the input, we just have to consider what the current state is. So what this looks like, I'll do this in purple, I guess. Yeah. I don't know if pink will show up better or not. You know, purple probably would be better. So the output, if you remember from our state diagram, is 0 in every case except for state E. So what this looks like is 0 for everywhere except for once we get here to state E. We go up to a 1 and back down to a 0. Now notice I drew this a little bit after the triggering edge because it's going to trigger with the state register. All right. So just like the state register, it's going to have some delay. Not much, but some. Yeah. So that's your basic timing diagram. Other things they might have gotten into, or I guess if you have any questions about this, you can ask, obviously, but the only other timing stuff that I can think of is like delay time for transistors. So every transistor, or not transistor, but logic gates. So I'm going to go and erase this. Or there you go, I'm just going to flip it over because we're essentially done with this now. Every logic gate has some sort of delay associated with it. So T delay is equal to T, I'm not going to try and spell the whole word, but it's called intrinsic delay. This means the delay that's based on just how the transistor, or how the whole thing is built altogether. And it's going to have units, usually units in nanoseconds. All right, or at least some time units. It's also, T delay is also going to equal the intrinsic delay plus T load times the capacitance of the load. All right, so the T load is going to be given in units, nanoseconds per femtofarad, and the C load is just going to be in units of femtofarads. So when you multiply these two together, the capacitance will cancel out, and you'll just be left with some like time constant. So what this looks like is, if you have an OR gate that drives two inverters, I'm just making this up. So the delay of the OR gate is going to have so some intrinsic delay. We'll say for the OR to two seconds per femtofarad. This would all be stuff that's given to you in some sort of table, like some, it'd just be a whole chart giving you a bunch of input capacitances, delays, or intrinsic delays, things like that. And then we'll say for the inverter, the input capacitance is, so capacitance N is equal to 3 femtofarads. All right, so the delay for this one here would be 2 nanoseconds. So T delay is equal to 2 nanoseconds for the intrinsic delay of the OR2 plus 2 nanoseconds per femtofarad. So 2 nanoseconds per femtofarad times not just the 3 femtofarads, but notice this one's going to have 3 femtofarads and this one's going to have 3 femtofarads. So it's going to be 6 total femtofarads. So is equal to 2 nanoseconds plus 2 nanoseconds for each femtofarad that's in here. So that's 6 total, so 6 times 2 is going to be 12 nanoseconds. which in total is going to give you 14 nanoseconds. All right, so these questions are fairly straightforward. It's just weird if you haven't seen them before. So again, this was something that they hammered a lot when I took it. If your professor never talked about this, then you know, disregard. But just in case you haven't seen or you saw this and didn't understand it the first time, now is the chance to ask some questions about it. So if there's any questions, I'll go back to it, but if not, I will move on to it looks like the next thing on his list was data path elements. So I'm going to erase this. I don't think there's any questions about this time diagram. Okay. He went over this in one of the lectures. Okay, cool. That's good to know. It has been a long time since I saw anyone have a question about that in the tutoring room. So, data path component like ROM. ROM wasn't on his list. His list said adders, subtractors, counters, shifters, multipliers, and floating point arithmetic comparators. So, it didn't have ROM on the list. If he covered that recently, it might be worth studying, but I was just going to cover the stuff that's on his list. Well, the first thing on his list was adders. Adders should be kind of reviewed from digital systems, the 2310 class. So if you have a half adder, so we'll start with a half adder, we'll build up to the full adder, and then there's kind of a system to this. So we'll start with a half adder. So half adder has inputs A, B, and output sum. So if we have 0, 1, 0, 1. So if we're building the half adder, we have 0 plus 0, it's going to give you 0. 0 plus 1 is going to give you 1. 1 plus 0 is going to give you 1. And then 1 plus 1 is going to give you a 0, but carry. So I'm going to call it carry out. And I'm actually just going to simplify this down to an S, because I don't want to write sum a bunch of times. That is a terrible S. That's a much better S. So, and then carry out here is going to be a 1. It's going to be 0 in every other case. So, yeah. So this is our half adder. Looks like we're buffering, or at least I'm buffering. Okay. I think we're good now. Okay, my phone buffered a little bit, so I'm just gonna say that we're good now because it looks clear. at least on my phone that I'm monitoring it on. Okay, so yeah, this is our half adder. And the only difference between a half adder and a full adder is that you consider where this carry out goes is it goes into a carry in. So carry n, which has 0, 0, 0, 0. So I need to build the rest of this truth table because now we have 3 inputs to the circuit. Alright, so now I've built the rest of my truth table. And I need to consider what happens in the bottom half. Alright, so the top half remains unchanged, but the bottom half we have to consider different stuff now. So what happens if you add 1 plus 0 plus 0 is you'll get 1 with no carry. 1 plus 0 plus 1 is going to be 2, so that's going to be a 0 carry a 1. 1 plus 0 is the same thing. It's going to be 0 carry a 1. And 1 plus 1 gives you 3, which is 1 carry a 1. Alright. So this is your full adder circuit, or your full adder truth table. Cool. Oh, nice. That's good that the camera glitch has stopped. It's been a weird thing with this camera. It's really good resolution, but it's, yeah, hasn't been great. So we don't draw the circuit for this every time. What we always do is we just put a box with the initials FA in it, all right? And then the variables that go around it. So it's usually A, B, carry in, then carry out, and S for sum. So it's usually a box that looks like that. It looks like it belongs on a periodic table. Now it really looks like it belongs in a periodic table. And yeah. So let's look at what a 4-bit adder would look like. So I'm gonna erase this. Just know that what happens inside that box follows this truth table. Is basically all you have to know. So if I want to build a 4-bit adder, I need to have 4 adders inside of it. Let's see, I'll build it on this side. I'm going to erase this one. So these are all full adders. Well, they don't all have to be full adders. This one can be a half adder if you're only building an adder. But I'm setting myself up for later, so I'm going to just call it a full adder. All right, just for simplicity. Every one of these looks the same, so it has inputs A, B, carry in, output, carry out, sum. All right. Okay, so we're building a full adder. So one thing is, starting at this one, every carry in needs to be fed by the previous carry out. So every one of these carry ins needs to come from the previous carry out. And it ends at this one, where this carry in needs to be a 0. Because if we're just building an adder, we don't need to carry anything in to start out with. Or just a 4-bit adder, we don't need to carry anything in. Okay, the outputs will look like this, where this is our MSB, this is our LSB. All right, most significant bit, least significant bit. And then since we have it in this order, whenever we finish, we'll just read our outputs out left to right, and that'll be our sum, so to speak. The inputs we have are here. And so we'll have A3, B3, A2, B2, A1, B1, A0, B0. And so what that looks like is if I were to add 3 plus 4, or I think I did 3 plus 4 yesterday. I'll do 5 plus 4. So why not? In fact, that'll even let us use the MSB. So if I have 5 plus 4, what that means is we'll just say A equals 5, B equals 4. Okay, so on A, we'll input 5, so it's 0, 0, 1, 0, 1. B is going to equal to 4, which is 0, 1, 0, 0. And so at this point, we just go through and treat the adders like they're adders. So 1 plus 0 is 1, carry a 0. So 0 gets fed back around 0. So 0 plus 0 plus 0 is 0, carry a 0. So 0 gets fed up to here. 1 plus 0 is going to be 0, carry a 1. So the 1 gets fed up to here. And 1 plus 0 plus 1 is 1, carry a 0. So my output ends up being 0, 1, 0, 0, 1. Which, if you turn that into binary, equals 9, which is what we expected, having 5 plus 4. All right, so that's good so far. Next thing they have on here is subtractors. So the trick with a subtractor is that you need to turn one of those numbers into 2's complement. And let's just say that we're going to turn B, like the input B. We're going to make that a 2's complement. So in order to do 2's complement, you need to do two things. You need to invert all the bits, and you need to add 1. All right, so I'm going to invert all the bits. Did you take my marker, buddy? Oh, no, that's not it. I think my cat took my marker. Right? I don't know where he did with it. Well, looks like I don't have a black marker anymore. Oh well. We'll do it in brown. It's kind of dark. So what I'm going to do now is invert all of the B inputs. Can't tell if he still has it or not. So all the B inputs here, I'm going to invert them before they get to the full adder. Okay, so now B is feeding in an inverted B, so every one of these is going to equal to B naught. Okay, the other half of 2's complement is that you need to also add 1 to whatever you invert. And since there's no really good way to do that outside the circuit, what we can do is inside is we can make this carry in bit 1. All right. So if we carry in 1, let's look at what happens if we have 5 minus 4 at this point. So what we're going to solve for is 5 minus 4. same deal. Like we're gonna send in the same inputs. We're gonna have 0, 1, 0, 0. Okay, B is still gonna equal 4. It's just the way we built the circuit now looks more like a subtractor than an adder. That is a potentiometer, buddy. Okay. Okay, so let's work through this. Every one of these inverters is just going to invert whatever the input was. So this 0 is going to become a 1. This 1 is going to become a 0. This 0 is going to become a 1. It's going to become a 1. Suddenly, actually, whenever you have subtractors, this is no longer the MSB. This is just a throwaway value at this point. Reason being that this is your sign bit. So sign bit. Okay. So that carry out final thing only applies if it's just an adder. It doesn't always hold if you're subtracting. Okay. Let's see, some of these are going to change also, so I need to change what, erase this stuff before I get started. I also need to erase what the carries were. Okay, so now I think I'm ready to get started. So I've got, so far I have all the inputs A filled out, so it's 0, 1, 0, 1 for A. For all the B's, I have them inverted, so 0, 1, 0. Right? Oh, yeah, 0. So 0, 1, 0, 0 is 4, which I invert to become 1, 0, 1, 1. Okay, so starting on the first full adder, I have 1 plus 1 plus 1, that's 3. So we have 1 carry a 1, so this 1 gets carried up to here. This 1 plus, or 0 plus 1 plus 1 is going to be 2, so it's a 0 carry a 1, so this 1 gets carried around to here. This one we have 1 plus 0 plus 1 is going to equal 0 carry a 1, or 2, so 0 carry a 1. This one gets carried up to here. And we have 0 plus 1 plus 1 is going to equal, again, 0, carry a 1, but this one gets thrown away at the end. So what this gives us is, if you look at the outputs, we have 0, 0, let me erase, this was the result from the previous, when we did the addition. This is 0, this is 1, the output reads 1, which is 5 minus 4. So we did it right. So that's your subtractor. One trick I've seen before is some classes like to ask if you can build an adder subtractor, which means some circuit that looks to see if you have, if you want to add or subtract, like it can do both functions. And the way you do that is utilizing some properties of an XOR gate. So let me erase some of this stuff down here. Erase my values. Alright, let me also erase these inverters because they get replaced with XOR gates. This is no longer just type 1. So basically, this whole thing hinges on having a another input called S, or right, or I'll just call it sub, I guess. I don't know. So I'm going to replace all those inverters with XOR gates. All right, so B is going to tie into one of those inputs of the XOR gate. The other input's going to tie into the sub input, and then the sub input's also going to tie into the first carry in. Okay. No questions so far. So the nice thing about XOR is you can also think of them as conditional inverters. So if you look at the truth table for an XOR, so call the inputs B and sub. So 0, 0, 0, 1, 1, 0, 1, 0. I should switch these. So if we split this in half, all right, if you look at this as two halves, the top half is where you're XORing B with the input sub whenever sub is equal to 0, and the bottom half sub is equal to 1. All right, so if you look at how the XOR follows B, all right, so B is the thing that changes, sub stays the same. So as long as sub is 0, the XOR follows directly what B is. So if sub is 0, the output of this gate is just going to pass B, whatever the input was. However, if sub is 1, this XOR gate is going to act like an inverter, and that a 0 turns into a 1 and a 1 turns into a 0. So that's the trick with the XOR gates, is that if you XOR with a 0, you get whatever you input as the other input. And if you XOR with a 1, you're going to basically output the inversion of whatever you inputted. So yeah, so this is your whole adder subtractor circuit. And then the nice thing about this is that if sub is 1, we have the carry in of 1. So remember how with subtractor we have to also carry in, you have to carry in that 1. Well, that's how we get it there. And if we're adding, then sub is 0, so you're carrying in a 0 anyways. So that's the nice benefit of having a full adder. That kind of just makes the circuit a bit easier. Okay, so I think this is good enough on adder subtractors. Unless anyone has any other questions, I will move on to counters. So for counters, generally speaking, I use D flip-flops all the time, except for counters. Counters are the only time I use a T flip-flop. If you want me to cover the difference between T flip-flops and D flip-flops, let me know, I'll cover them. However, I did talk about them quite a bit yesterday in yesterday's thing. That was probably close to like 45 minutes into the review at that point. But yeah, it's getting kind of hot in here. I need to take my jacket off before we keep moving. But let's see. So with a counter, just basic counter, I'm just going to do, I'll do 4 bits. So the general structure is, I guess I go over here. The T flip-flops all the way through. Input clock. Output Q. Okay. The first flip-flop, so I should mention this is your LSB, this is your MSB. Alright, so that's your most significant bit, that's your least significant bit. All these clocks, I'm not going to draw them, but they're all tied together, so they all clock synchronously. They're all synchronized. Yeah. So the first thing is this first input is always equal to 1. So we just always clock. Also, okay, do you need me to cover mod counters at all? Has he talked about that? Let me know in the chat. And if he does, then I can just cover that. But if not, I'm just going to cover the easy way. Or the easy counter. I'll go and get started on the easy counter. So this 1 tells me that every clock edge, this first bit toggles. So after every clock edge, this bit's going to change. So 0, 1, 0, 1, 0, 1, every clock edge. This next bit is going to toggle. We're going to want it to toggle when every previous bit is a 1. And that's going to be true for every bit here, is we want it to change whenever all the previous bits are equal to 1. So I don't think you did. Okay, then I'm not going to really mess with that too much. They're not bad, it's just, I don't. If anyone has any questions about them, just let me know in the tutoring chat. I'll do that later, but I'm not going to do it in this video because we have other things to get onto. So for every one of these bits, we want it to toggle when every previous bit is equal to 1. So the only previous bit for this one is this bit here. So we're just going to tie the input straight to the Q, the output of the previous bit. So whenever this bit is a 1, it's going to tell this this bit to toggle on the next clock edge. All right. For this one, we want it to toggle again when every previous flop is a 1. So the way we do that is we put an AND gate here, feed it into this. We AND both this one, or the next previous flop, as well as the input to the previous flop. Okay, so the input to the previous flop will only be a 1 whenever every bit before this flop is a 1, and then this will only be a 1, or I should say this AND will only output a 1 whenever every previous bit is a 1, as well as the previous flop being a 1. You kind of get what I'm saying? I kind of butchered that, at least wording wise, but that's the gist of it, at least. So yeah, so that is how we tell this bit when to toggle. For this bit, it's the same thing, where we have to AND both the previous bit as well as the input to the previous flop, which is right there, and we send that directly into T. Now where we probe our outputs is at the output of every flop. So this is going to be out 0, out 1, out 2, and out 3. Again, remember this is your most significant bit, this is your least significant bit. So if you were to count up to 5, so if you clocked it 5 times starting at 0, the first thing it would be is 1, 0, 0, 0. All right, now 1, 0, 0, 0 may look like binary for 8, but you have to remember that this is your least significant bit, so you actually read it backwards, where it's 0, 0, 0, 1. All right, so if you clocked it 5 times, you would read 0, 1, 0, 1, which, while if you just read it left to right, looks like binary 10, you have to read it backwards where it's binary for 5. All right. So yeah, that's counters for you. Next thing I have in here is shifters. So shifters, I want to move on from counters and go into shifters, where you just have basically a register where you can tell it to shift some number of bits to the left or right. So a shift register, generally speaking, I'm just going to do 4 bits like I normally do. So you'll have inputs D, Q. All right, for registers, I like to use D flip-flops all the time. You can kind of use, you can use D flip-flops and T flip-flops interchangeably. It's totally possible to make them work. However, some cases are just easier to use D flip-flops, whereas some things like counters are just easier to use T flip-flops. So, you know, just know the application, know which one you're going to use. So you have D, Q, Q. There's also a Q naught bit in every one of these flops, but we don't really worry about it very much because we mostly just care about what the current state is. It's just easier to think of things like that. But it does exist in pretty much every flip-flop you see. So yeah, shift register, let's just say that this is your, we'll say this is our MSB, this being our LSB. Let's say we want to shift input so we'll have some input that we're shifting in. Every Q is going to feed into the next D, and this Q is just going to go off to nowhere. I'm not going to draw them, but we're going to assume every one of these clocks are tied together. Yeah, we're just going to go with this. So let's say our input sequence is, or let's say our initial values are 0, 0, 0, 0. Okay. I'm not going to draw them, but we're going to read off of the Q output of every one of these flops. So if I input a 1, so if I input a 1 just one time for one clock sequence, the first clock it reads, so this 1, is going to get shifted into this place here. So I'm going to change colors to blue, and this is what it's going to look like after one clock sequence. We're going to go back down to 0 at the next clock edge, after the next clock edge. This 1 is going to get shifted into this register. It's going to go there. This 0 is going to get shifted into this register. It's going to be there. This 0 is going to get shifted into this one, which is there. This 0 is going to get shifted to here, which goes there. All right. So, see how do we call this? It's like, remember there's like an acronym for whenever you shift in, I think it's FIPO or SIPO, serial in parallel out. I think this is what serial in parallel out looks like. So I'm reading everything in serially, so one at a time, but when I look at my outputs, I'm looking at all 4 at the same time. Okay, so I'm saying that my outputs are at every Q is what I said at the start. So this would be SIPO, serial in parallel out. All right, so this is how it is here after, say, another clock edge. Say we're still shifting in another 0. So if we shift in another 0, this 0 is going to go here. This 1 is going to go to this register. This 0 is going to go to this register. This 0 is going to go to this register. And this 0 is going to go off to nowhere. All right, so after, so to start out with, we had 0, 0, 0, 0. At our first clock edge, we had, or after our first clock edge, we had 1, 0, 0, 0. Then after our second clock edge, we had 0, 1, 0, 0. All right. We'll go 2 more clock edges. That should be all. So the next clock edge, we shift in another 0. This 0 goes here. This 0 goes here. This 1 goes here. This 0 goes to here. And we have 0, 0, 1, 0. And then the last one, we'll shift in another 0. This 0 goes here. This 0 goes to here. This 0 goes to here. This 1 goes to here. This 0 goes out to nowhere. And so we end up with 0, 0, 0, 1. Make sure there's no questions. Good so far. Okay. So if you look at, just ignoring this first one here, if you look at what happens to our output, so this was 1, 0, 0, 0, so that would be 8, right? So this, if you translate from binary to decimal, would be 8. From here, it would be 0, 1, 0, 0, which would equal 4 in decimal. 0, 0, 1, 0 would equal 2 in decimal, and 0, 0, 0, 1 would equal 1 in decimal. Okay, so what this tells us is that every right shift you do divides by 2. Similarly, if you want the opposite direction, so this would look like shifting to the left, every shift left you do multiplies by 2. So if you want to multiply by 4, you would shift left by 2. Okay, so that is shifters, and then it kind of set me up for multipliers. So I'm going to look at what happens if you want to multiply by something that's not a power of 2. Oh, and I should also mention that if you have a shift register, we usually draw them as just a block like this. And let's say it was left shift, so we would put arrows to the left and then the amount. So this would mean left shift by 1 in this register. Oh, there it is. Okay. So this would be a left shift by 1 register. In other words, the output of this will be 2 times the input. Okay. And another thing you have to remember is if you have an input of, say, 8 wires, the output needs to be 9, at least 9 wires long. And the reason is because if you shift, you might lose some data by shifting it out of your shift register. So if you shift in 8 bits, you need to have 9 bits coming out of this shifter. I didn't have that in this one. I kind of just said it went off to nowhere. But if you want to preserve data, it doesn't just go off to nowhere. And if you're going to be designing something, you want it to preserve data. So, yeah. So I think that is everything on shifters. Now I will talk about multiplier. So what happens if I want a circuit to give me, or what happens if I want to multiply 6 times 3? Actually, no, I did that in yesterday's example. We'll do 9 times 5, or 7 times 5. So what happens if I want 7 times 5? So I'm just going to say this is the input. This is going to be what we want the circuit to do, is multiply by 5. So this is going to equal to 7 times 4 plus 1. All right, this is equal to 7 times 2 squared plus 2 to 0. So this is equal to 7 left shifted by 2 plus 7 left shifted by 0. Left shift by 0 is just 1, or it's just itself, right? So in other words, we want our circuit to take an input 7, left shifted by 2, and then add it with itself. So if you were to draw this as a circuit with just an arbitrary n by 5 kind of thing. So if we have an input going in, we'd want to do two things. We want to shift left by 2, and then have a full adder which adds it with itself and outputs some number there. Okay, so this is how you build a circuit that takes some input, multiplies it by, so the output would be 5n there. Okay, now what happens if the input is 32 bits long? Well, if you have 32 bits and you shift it left by 2, that means the output of this needs to be 34 bits long. And if you're adding a 34-bit number by a 32-bit number, your output needs to be at least 1 bit more than the biggest input. So this needs to be at least 35 bits wide. All right. So every full adder, the output needs to be at least 1 bit wider than the biggest input. And every shifter, if it's a shift left, it needs to be at least the number of shifts that you have bigger than the input. Cool. So going to the full adder, we had a 34-bit number plus a 32-bit number, so we had to add 1 to 34 to give us a 35-bit. All right. Doesn't say dividers, so I'm not gonna really cover that too much. If you need a divider example, I did them yesterday. Gosh, I would have been kind of closer to the end whenever I did dividers. The only thing left on data path elements I had was floating point arithmetic comparators. But I think that comes back to understanding floating point numbers. So floating point numbers, you have a sign bit, you have some exponent, and then you have some what's called a mantissa. Okay, I don't know if I spelled mantissa right or not, but basically the first thing you check to see which one is bigger is, I would say the sign bit, because if one bit is positive, if one number is positive and the other is negative, then it's be pretty clear which one is the greater than number. Next thing you check if both sign bits are the same is the exponent. All right, so if both sign bits were 1, you would need to check if the exponent, you need to see which exponent was smaller, basically. So that's another thing is in a floating point number, the sign bit, so your numbers won't be written in 2's complement. Everything after the sign bit will be purely the magnitude of the number, and the sign bit will just tell you if it's positive or negative. So, you know, the only difference between like -1 and +1 is going to be the sign bit. So, just so you're aware. I'm not going to get too much into building these 2's complement things because I doubt that's going to be on the test, but it's important to just kind of understand the general idea of it because it's a bit more complicated just throwing numbers into this and just seeing what comes out. So again, if the sign bit is the same and the exponent is the same, the last thing you check is the mantissa. And again, just be wary, if you're looking at a sign bit where they're both negative, then the greater number is going to be the one where the mantis is smaller. All right, versus if the sign bit were both zeros, meaning they're both positive numbers, then the bigger number is going to be the one with the bigger mantissa. All right. So that's kind of all I'm going to cover on floating point arithmetic comparators. I think the comparator is just a circuit that you might have to memorize or have in a cheat sheet or something like that. Because I don't have it memorized. I don't do comparators almost ever. But yeah. At least not digital comparators. All right, so the next, I guess actually kind of the last thing on my list is electrical properties of logic gates. And the four things he said was noise margin, Cmos gates, time delay, and power. Okay, so start with noise margin. I kind of covered time delay already. And the power is basically just like one equation to learn. I think it's like capacitance times the voltage, I think gives you power or energy or something like that. So I'm just going to cover noise margin and Cmos gates, since I've already done time delay, and power should just be one equation. I guess I kind of flipped this board over, but oh well. If you have any questions, obviously just drop them in. I haven't seen any questions in a while, so I am checking. But if I don't see any questions, I don't see a reason to stop. So I've got a Red Sox game I gotta watch, or it's kind of already going, but you know, gotta hurry up through this so I can watch my Red Sox play. So noise margin, let me see, I have notes so I make sure I get everything exactly right. So we draw this on a scale between, so this is your supply voltage, or VDD, and this is your base voltage or ground. Sometimes it's also called VSS. So VSS and ground, those are interchangeable words, at least in logic gates. In the industry, I've never seen it called VSS. I've only seen it called that in some circuits classes. So it'll almost always be called ground. Okay. So we have some definitions to go in here. The first one is VOH. So VOH. Okay, drawing this, so keep in mind this is going to be higher voltages, that's going to be lower voltages. So VOH is the max. Is it max or is it min? Okay, it's min, yeah. I thought it should be min. It's going to be the minimum out voltage for logic 1. In other words, if your gate is trying to output a 1, the minimum output voltage it's going to send is VOH. All right. Next we have VIH. Make sure I have this right. Yeah. So VIH So this is going to be the voltage, or the input high voltage, and this is going to be the minimum in voltage for logic 1. Okay, so what this means is that if your gate is looking for a 1, the minimum voltage that it can be to register as a 1 is going to be this VIH. Okay, it's important that the VOH is higher than the VIH because in order for a gate to receive a 1, that means that it needs to receive some voltage that's higher than okay, cool. I can keep going. That means it needs to receive a voltage that's higher than what it's expecting a 1 to look like. Okay? And as long as the voltage being output from a previous gate is higher than that, then this is going to receive a 1. So yeah, this area in between here is called the noise margin, or the high noise margin. And I believe, yeah, it's just N M sub H. So this is your high noise margin, is the difference between, would be VOH minus VIH. All right, and it's a similar story down here. So you have a V in low and a V output low. So this is going to be VIL. It's going to be similar, except it's going to be the maximum input voltage where your gate will treat it like it was 0. Okay, so anything below here, so from this point onwards, is going to treat the input as a 0. And anything from here onwards is going to treat the input like a 1. So, and it's important that the voltage output low is lower than the voltage input low, because if it's supplying, or if you're sending something, you need it to be lower than what that gate's going to treat it like a 0 to be. Okay, I'm not going to rewrite that whole definition out for this stuff. It's very similar. It's just this gets changed to max, and that gets changed to 1, and they correspond input and output. Or that gets changed to 0, I should say. So yeah, that, and I should also mention this part here is going to be your noise margin on the low end. So that's how you find your two noise margins. I've never seen noise margin refer to anything else. I assume that's what they're talking about when they say noise margin. You have to let me know if you actually covered this much in class. When I took this, my professor, they barely touched on this, and I think it might have been one question on exam, but it was one of the earlier ones, so I'm kind of surprised it's showing up on the final. But, yep. Next thing I have is Cmos Gates. So that can kind of refer to a bunch of different things. So I'll just cover all of them. Because I love Cmos Gates, they're fun. You just need to smart and flip the board over. Some other questions. 4 people in the watching though. I think one of them counts as me. Let's see if I scroll at all, does it counts more? Nope, still 4. That's about the same as we had yesterday. I think the high I saw yesterday was like 6 or 7. So, yeah. Did I drink all? No, I didn't. Okay, Cmos Gates. So CMOS refers to the type of transistors used, or combinational MOS, MOS is short for MOSFET. MOSFET stands for metal oxide semiconductor field effect transistor. If you're playing Jeopardy, then that might show up and you'll know it. But that's about all there is about that. So CMOS, there actually is only two types. You have what's called the NMOS, which don't have an inverting bubble, and you have the PMOS, which have an inverting bubble. So NMOS, PMOS. Very rarely they'll be drawn with an arrow on them, like this. So the NMOS will have the arrow going out of it, the PMOS will have the arrow going into the gate. The arrow always points in the direction of current. However, in this class, I'm pretty sure they just never draw the arrow. So that's only ever really done by some weird software, and you'll see it in your circuits class, electronic circuits, whenever you take it. So yeah, those are your two NMOS, and the way they function is when so this is your gate. So the gate is the part where it goes into the transistor from the side, right? Or it goes into the part that's separated from the rest of the transistor. So when your input to the gate on NMOS is a 1, this conducts. So equals 1, and this conducts when your VG equals 0, or logic 0, I should say. I'm talking completely about digital logic, not actual voltages. So you can think of them as switches that you can control, where if you input a 1 to an NMOS, it closes the switch, right, or latch, or whatever it is. And then for PMOS, if your input's a 0, that closes the latch. And then the opposite case, where a 0 on an NMOS opens the latch, doesn't allow current through. I don't really like to call it current, it's kind of different, but the effect of current going through, and then a 1 on a PMOS opens the latch, basically. So how do we use this to our advantage? Is we can build logic gates with them. So we'll start simple with the inverter. The inverter has 1 PMOS, 1 NMOS. Okay, so this is your inverter. I have power, ground. That's just how we always draw them, is a line with the VDD over it for power and then the downwards arrow for ground. If I input a 1 to this, so if I input a 1, it's going to leave this open but close the circuit that goes to ground. So inputting a 1 outputs a 0. All right, similarly, if I input a 0, I'm going to close this circuit and open this one. So this is going to be open, and we're just going to have a closed circuit to power. So inputting a 0 outputs a 1. So that's your inverter. Next thing we can try is let's see, how do I want to do this? What if we want a AND gate? Just curious, did your professor talk any about why inverting gates are better than non-inverting gates? I'm going to start drawing the AND gate, but just let me know in the chat. So an AND gate will look something like this. No answer yet. Okay. So this is your AND gate. It's not how you would ever actually build an AND gate, because you don't want your PMOS to be going up to ground or up to power, and you don't want your, I said that backwards. You don't want your NMOS going up to power. You don't want your PMOS going down to ground. And that just has to do with electrical properties of Cmos gates. Because that's kind of just a whole another can of beans. I don't want to open that yet. That's not really what this class is about. I can cover it if he's gotten into that, or if you want to know, but just that's a rule that you must follow, is that PMOS don't go to ground, NMOS don't go to power. Except we're going to build it here because this is just the best way to visualize an AND gate. So notice I have these two transistors in series with each other, meaning that the only way to get to power is by both of them being closed. The only way both of them be closed is if both A and B are 0, or both are 1. Okay. So I don't remember what those messages were applying to. So if both of these are 1, we're going to have a closed path to power, and if both of these are 1, then this will be open, this will be open, and so we'll have no path to ground. All right, so let's consider other cases. Let's consider if A is 1, B is 0. So if A is 1, this will be closed, but this will be open. So we don't have a path to power because this gate is open. If A is 1, B is 0, so this will be open, but this will suddenly be closed because B is 0. So we'll have a path to ground. All right, so and you can go through and you can see that there's no digital input that you can put into this to where you have a path to both power and ground. And that's where the whole idea of combinational logic comes from, is that there's sort of a De Morgan's law happening between the NMOS and the PMOS, where there's no way that you can, there's no way that both the pull-up network and the pull-down network are both connecting at the same time. See, how do I say that? Okay, so the pull-up network, we would represent that with A and B, right? So A and B. Now, if I want the pull-down network, that would mean that we invert. So pull up equals this, pull down equals the inversion of the pull up network, which can equal A NAND with B. If I apply De Morgan's law to this, this would be A naught or B naught. So A naught would be a PMOS transistor, or or B with a PMOS transistor, right? B naught would be another PMOS transistor. And then ORs are represented with parallel branches. So this tells me that A naught in parallel with B naught mean A going into a PMOS transistor in parallel with B going into a PMOS transistor. So, you know, that's your proof that there's no way that you're going to have both conducting at the same time. Okay. Some other things you can do is, if you want to make this into a NAND, so if you want to make this into a NAND, the way to do that is to actually kind of flip it upside down. Let's switch to power and ground. All right, I need to rewrite my inputs as the actual. So this is out. This is A, B, A, B. All right, everything's all the same. It's just, it's upside down now. So this, as it is right now, would be a NAND gate. And that all I've done is I've changed where my power and ground is from the previous circuit. So yeah, simple enough. And the same thing would apply if I were to draw an OR gate and then switch it into a NOR gate, is I would just switch power and ground again. If I want to make an OR gate, so BDD, so we have this goes into, so I'm building an OR gate. Out from here. So this would be A, B, A, B, your output. All right, so as you can see, if you input a 1 to either A or B, that's going to close one or both of these circuits. All right, and so you'll have a path to power. And if you input a 1 to either A or B, that's going to open either of these here or both, which means that you won't have a path to ground. Right? So similarly, if you wanted to make a NAND or a NOR circuit, I guess you could say, all you do is just basically turn this upside down and switch where your power and ground is at. So you would have I'll just draw it here. So if I were to draw this upside down, then I have series stuff up here. Okay, so Cmos are still the series things. The NMOS are still in parallel, just like before. Outputs from the same place. The output will always be between the NMOS and the PMOS, or it'll always be between the pull up and pull down networks. Make sure there's no questions. Nope, still good. So yeah, this is literally the same thing as before, right? We have PMOS in series. We have NMOS in parallel. Output comes from in between. The only difference is VDD and ground basically switch places. Like the VDD is now tied to the PMOS, the ground is now tied to the NMOS. And for the purposes of this class, it's just good to know that that will give you a better performing circuit. Okay. I don't really have anything else on my list. Is there anything else you need? Any questions along the way? Guess I'm gonna hang around for a couple more minutes. I'll probably just hang around till 8:20, I guess. I feel like I'm finishing this faster than I did yesterday, but I think yesterday went like 2 hours 45 minutes, I think. This only went 2 hours 15 minutes. So but I actually had some technical difficulties yesterday. For some reason it won't let me stream and watch my stream on the same computer, so I have to use my phone. It took me a little while to realize that. So I will go in here for a little while. You pretty much covered everything I had questions on. Thank you. Bye. Thank you, Hassan. Thank you for dropping by, hanging out on a Thursday night. Appreciate the feedback. I'm not sure if Eric is still in the chat, but you'll all be sure to thank Eric for the great job he's done this, not just this semester, but since he took over the head tutor role. Right now he's going through the gauntlet, which is VLSI, so that's why I'm helping out with him. Helping him out a little bit for this final. I remember how much fun VLSI was, so I am very happy to help. And thank you, Hassan, for being active in the chat. It says there is one viewer. Oh, I think it's me. All right. I don't believe there's any other questions, but if there is, let me know in the tutoring room on Discord. Down below. Say bye, Elton. All right, I will see you all later. Bye.